Today we're going to be graphing this parametric curve on this three-dimensional graph I have created, the tactile graph. So this is a model of, I have z-axis, I have my x-axis, and I have my y-axis here. I have 8 octants is what we call it when we're dealing in 3 dimensions. So I have 1, 2, 3, 4 times 2 because I have 2 hands, octants. And I'm going to show you how I use this to graph just a simple parametric curve. I shouldn't say simple. It's not that easy. And that's honestly why I created this tool, because I really don't think it was easy to learn how to do this without this tool. And so I didn't. So join me over here on this whiteboard and I will draw for you some math, and then I'll show you how I use this tool to graph that math. Because we have a variable t, I'm going to choose this interval 0 to 2 pi for this variable. And then within our function, we have these, I suppose I need to, let's be so explicit because this is a tutorial, y, z, we have these vector values for that. So that just means that there's this parameter t that I'm changing across. So each of my variables changes along this parameter. And that just enables us to get this cool 3-dimensional graph. Okay, so starting with the intercepts, I have this unit circle graph here. So this unit circle, it just has all of these coordinate points for where we're looking at on the unit circle, and then it also has the radian value. So I'm going to be using radian values for my t parameter, and the coordinate points that come out of that radian value are going to be what I plug into my vector value function. And I do get this a lot where we get confused as far as there's x, y, z here, right? These are my variables. And then there's these x's and y's coordinate points on our unit circle. So just keep in mind, these are 2 separate graphs, right? This is one graph, and the graph I have over here is another graph. So we're not talking about the same x's and y's. So if you're hearing me say a lot of x and y's, I'll try to be specific as far as if it's the unit circle x or y, and I probably won't refer to these so much as x's and y's, just to help us not get so confused. But that is one of the main things I hear when people are confused on these vector valued functions and all these parameters. And it keeps it nice and neat when you can see it, that this is a separate x and y graph. We have literally separate axes here versus the other guy, which is completely separate axes. They might be the same color, but that's just for my own brain. But completely separate x's and y values. All right, so let's jump in. I'm going to try to find within this interval where intercepts live. So we can do that by looking at our unit circle and finding all of these 0 coordinate points. So I have 1, 2, 3, 4. And then their adjacent radian value is going to be what we want to mark here in our t interval to identify where the intercepts might live. So the first one is going to be 0. So when t equals 0, we'll have a 0 in the y point on the unit circle. And then when t equals pi over 2, we have another 0 in that x coordinate. We have pi. We have 3 pi over 2. And then because we have a closed interval, that means these brackets exist. We also want to include 2 pi. So we're going to do a full lap around that circle, and we're going to come back to another 0. So I'm going to figure out what my vector valued function looks like at all of these points, so that way I can figure out which intercepts they live. But first, we might also want to identify too what octants are. So I already kind of mentioned that a graph has 8 octants when we're in 3 dimensions. And so I'm just going to identify what points live in what octants. And this will make it easy when we're graphing to see where we should be putting all of our points. We're going to have maybe a lot of points in this problem, so I'll just keep it straight. So I don't know if there's any logical way to iterate through these octants. So this is usually how I iterate through them when I'm labeling them. So I just choose one of them to be negative kind of across the board here. And then now I've got all the positives, I've got 1 negative, so then I'm going to do another negative. But I'm going to do 2 of them because now I want to find all the combinations. And then lastly, when everybody is negative, that's our last octant. So that's how I've iterated through them. I'm going to go ahead and label all the coordinate points we find as we go through this to see what octant we're working in. So the first one, when t equals 0, then I'm just going to start marking over here. I don't want to have to write out everything right here, but when sine of t, if t is 0, we're going to go to our unit circle. We're going to find the y value on the unit circle because that is the sine value here. And we're going to say, well, that's 0. Cosine is the x value on the unit circle, so that's 1. And then sine of 2t, well, 0 times 2 is still 0, so we're still here at 0. And then I'm going to look at this point, and I'm going to go, oh, I'm going to choose an octant. This is obviously when any of our y's are positive. So since this is only on one axis, this is just the y-axis, it lives in 1, 2, 3, 4 of our octants. So I'm just going to pick my favorite here to mark it. And we'll see how these 4 octants all contain the same number when we graph. All right, and then lastly, for all of these intercepts, we're going to choose t to be 2 pi. And so sine at 2 pi, we're just going to do a full lap, is 0. And then cosine of that full lap is 1. And then the sine value of 2 times 2 pi, so 4 pi, that's just 2 full laps around that circle, and it's 0 in that y's place there. So again, my y value is the positive one. And you can see these are actually exactly the same point. So that maybe tells us that our graph is going to do a little loop-de-loop and it's going to come back to this point since we did, in fact, do a loop-de-loop, right? A full loop around that circle. So as we graphed last week, if you remember, we had this wavy function here. This is that sine function. And there are some sine functions inside of our vector value function, and there is a cosine term. And so we might see this shape take place in specific octants. We might see that it reflects around each other. But what we can really expect is we're going to come back to one point. So maybe we're going to see something like this, but 3-dimensionally, so that it loops back around on itself. Alrighty, so I'm just going to choose octant 1, but really it's going to be any of the octants. That does not look like an O. Sorry, being left-handed and using a whiteboard is kind of hard, but I live, I learn. Alrighty, we have found all of the intercepts. So now let's move on to deciding our axis scale. Since I have all these 1s and -1s, and my unit circle values are all going to be less than 1 here on these coordinate points. And even if I did 2 times that unit circle radian value, I still, as you remember, I just did 2 full loops. So I'm never escaping outside of 1 on any of these points here. And so my bounds for my graph, I can decipher just from using my unit circle that it's going to be between 1 and -1. I suppose we should usually flip that. So -1 and 1. So if I want to choose my axis scale, I'm just going to choose that each whole, as you can see, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 holes. And so I'm just going to choose that each hole on my axis marks 1/10 of a 1. And that way I'm going to get a graph that maps on the whole graph. So I'm going to just maybe mark that up here, my scale. So is 1/10 for X, Y, and Z, because none of them are going to escape outside of 1. Alrighty, so continuing on, I'm going to go ahead and choose some values here on my unit circle. These are my yellow values for T to decide what points I'm going to grab. I'm just going to choose all of these yellow values just to get a really full picture of what we're looking at. You can obviously graph less. You can use the symmetry of this problem to end up graphing. You don't have to mark every single point, but I'm going to do it all explicitly to show y'all how I would do this naturally. So if I'm going to choose, I'm going to start with pi over 6, right? That's just the next. That is the next value on the radian side here. So t of pi over 6. That means we're going to start with a coordinate point here where sine of pi over 6, and that's the y value on that unit circle, so that's 1 over 2. And then cosine of pi over 6 is the x value, so we have square root 3 over 2. Sine of 2 times pi over 6, so 2 times pi over 6 is going to give us pi over 3. that is the y value here. So square root 3 over 2. And then looking at these values, we can see that this is octant 1. And then going to the next one, we have t equals pi over 4. Alrighty, so now we are going to graph. So as I just stated, we have 3 points in each octant and we have some intercept points. So I'm going to go ahead and choose 4 pipe cleaners because I have 4 octants that I'm working in. And I'm just going to set them off to the side. And then I have some like pre-labeled points that I was getting ready for this. So I'm just going to start off with the first intercept point we have, which is a positive y. So I'm going to find my positive y-axis, which is right here. And like I said, I'm going to mark it 1, 2, so let's go. This is my positive y, and I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that 10th one is my 1 value. And that'll just give us consistency around the board. So then now I'm going to look at the next one, which is my positive x. So now I'm going to take my guy here. You can do this a couple ways. You can choose to label each point individually. And so that's what I'm going to do. I'm going to stick some letter values on each of these points that don't have labels, and then I'm going to mark them on my whiteboard just so that I can keep track of everybody. So I've just got like A, B, C, D, C. A, B, C, D, E, all the letters. So let me get marking. Okay, everybody is marked with a letter, and I have like an extra 1 and -1 in there, I guess. That's because probably I want to mark maybe my z-axis. Since we don't have any intercepts there, I'm just going to label the z-axis with the same scale because I want to be able to understand what it is. There we go. And as we recognize from our problem, there was no z-value above 1. They were all 1 and -1 were their bounds, so we are doing good. Very symmetric graph here. And then I'm going to start with octant 1, and I'm going to take my pipe cleaner, and I'm just going to put these points in each. So I've got A, B, and C here. And then my octant 1 I chose to be when X, Y, and Z were all positive. So I'm going to find that octant, which is this guy right here. And then I'm going to find the intercept. I'm going to pull my cleaner through. And I'm just going to kind of wrap it through this intercept. I just don't want it to pull through when I graph it. So this just makes it rather stationary. And then I'm going to do the same deal here for this point. And then hopefully a pipe cleaner is it's enough to get us through that whole octant's worth of graph. So let's kind of pull it taut and test it. That looks right. And then I know that at the peak, my z is going to be 1. So that would be at the point B. And then I also have this point C where my z is probably like square root 3 over 2. So maybe like right below 1 because square root 3 over 2 is like roughly 8.66. So I'm just going to kind of twist my pipe cleaner so it stays stationary like that. I don't know if y'all can see this. I'm going to have to look at the footage. And I have another one. And then something that I like to do when I'm graphing these problems and like I have these pipe cleaners with these points is I like to use like scaffolding. I don't know if, so I've got these sticks here and I've got a specific point I have in mind, right? So it's going to be the square root 2 over 2 point here. So square root of 2 over 2 is roughly 0.7. So I'm going to go to the tens place. We have 1, 2, 3, 4, 5, 6, 7. So that's 7/10. I'm going to do that again. So I have 1, 2, 3, 4, 5, 6, 7. And that's kind of right here. And this scaffolding, it'll just make it so the graph will stay stationary. You don't have to use this. And in fact, when you get rather good at this, you maybe will find this a nuisance. But for now, I'm going to use it at least just to keep my points stationary for this tutorial. And also, as you can see, my pipe cleaner is not super straight, so I'm just going to try to kink it out. And I can kind of eyeball where one lives on the z-axis. And then here I'm just creating a kink in the pipe cleaner so that my little point will stay. Same deal for that one. Just using gravity here. And gravity is taking control. There we go. Okay, so that looks rather good. Like I said, you don't need the scaffolding stick, but I just find them a little helpful sometimes as I'm doing this when you're working against gravity. On the negative side, they actually stay pretty good, so I'm not going to use the scaffolding for the negative side, but the positive. Obviously, gravity wants to pull that stuff down, so it just makes it obvious that that's not what we intended. The next octant we're working in is the 5th octant, and so that is when x and y were both negative. So I'm going to find that, which is this guy right here. So this octant I'm going to be working in next. And in this case, z is still positive, so I'm going to have basically the same shape. It looks like they just reflect like that. So I'm just going to insert my pipe cleaner into my intercept points I've already put there. All right, and there you have it. That is the 7th octant, the last one in our graph. You can choose to make this in whatever order you want. You can choose to create it, and obviously it's not perfect, right? You're going to look at this and go, Miss Sandy, why do I need a tactile graph if Desmos can do this, and it's going to be so much prettier and so much more perfect? And I'm going to say to you, you don't need this. I need this. This is something I need because I'm a tactile learner, and building this with my hands and seeing it in actual 3 dimensions, not on a 2-dimensional surface, it fits in my head a little bit better. It works. It makes that 3-dimensional graphing make a lot more sense when I can count my octants, when I can see where things live. So if you're like me and you're a tactile learner, maybe this tool is for you. Maybe you would benefit from it. And if you're not a tactile learner, that's okay. Some of us just learn by constructing, and I have an intuition that a lot of people would learn more from constructing, but I do think that this tool is just missing from your inventory. So if you want this tool in your inventory, let me know. Subscribe to my channel. I would be happy to make more tutorials to show you how I use this to graph and make more imperfect structures like this one. This is the traditional parametric curve. This is a three-dimensional curve. It's not a surface, it's not a manifold, it's just the lines across the curve as we saw in our vector value function. So as I continue making more tutorials, I'll be making more with some surfaces. Somebody recommended some like matrices with their eigenvalues, so that would be cool. But there's a lot of math that can happen on this, and I'm really excited to do all the math. So please keep watching.